If I could have your attention, I think we're going to go ahead and start our program for the evening. By popular demand, we have back one of our speakers from previous years, and that's Don Pettit. And I think you got to know Don Pettit, certainly those of you that have attended the sessions these last couple of days. But if you didn't know Don, he's an astronaut that has flown both on the International Space Station on 2 missions and then also flown on the shuttle. And hopefully he'll get a chance to fly again. So let me turn it over to Don.
Thanks, George. If God intended man to be a spacefaring species, he would have given man a moon. This is one of my favorite expressions by a fellow by the name of Kraft Ericke from 1984. Kraft was one of the German rocket scientists brought here after World War II and did a life's worth of work here in America on our space program. And the thing I like about this expression is that it extends the classic expression, if God intended man to fly, he would have given us wings. And of course, we don't have wings, and we figured out how to fly anyway. And so now with the help of a moon, we should be able to become spacefaring species. So why the moon? I'm going to hope everybody remembers 3 things. The moon is close, the moon is interesting, and the moon is useful. So if you could remember those 3 things at the end of my talk, wow, that's good. So the moon is close. It's 3 days away. However, I had to come to the realization those are Apollo days. With Orion spacecraft, for some reason, it just doesn't have the oomph that we put in the Apollo, and it takes 5 days for Orion to get to the moon. So whether it's 3 days or 5 days, the moon is still close, and it can allow for resupply, spare parts, and even more important, it can allow for aborts, where even if your tail is between your legs, you're coming back to Earth because you had a malfunction of something or another, at least you're still alive. And that's an important thing from somebody that might have your pound of flesh on a vehicle going to the moon. So the moon, why the moon? It's close. Why the moon? It's interesting. It may not be interesting to everybody, but it is interesting. The moon is a legitimate place of study on its own right. It's a planetary-sized body. So people will talk about the moon as a planetary-sized body. That means it's large enough so mutual self-gravitation makes it into a spherical-shaped body. It will have processes, dynamic processes on it, indicative of what happens on a moon. There's magma events, there's volcanoes, there's all this stuff. There's grumbling inside of the moon, indicative of what happens with a planetary-sized body. The moon has preserved the history of our solar system in the Earth-Moon environment, and this history is obliterated on Earth. So we can go back to the moon, and for the early Earth period, we can find out about Earth. So, and that's another interesting thing. We go to the moon to learn about Earth. And then the moon is a natural laboratory away from Earth. You could use it as a stable structure for doing any number of other scientific experiments, where it's building observatories or going someplace where you don't have radio interference or whatever. The moon represents a natural laboratory free from an atmosphere. So the moon, for its own right, is a place of scientific interest. The moon, it's useful. It has resources to use. And these are resources that you don't need to take from planet Earth. And then it has low gravity. It's 1/6 of Earth's gravity. And what I'm going to do is I'm going to independently talk about the utility of the moon. I'm going to talk about resources to use. And then I'm going to go into a little bit of a diatribe on how we can use its low gravity. So, what are you going to do with these resources? And you'll notice that I've got all the latest NASA-generated computer fonts here that I've used for these slides. I mean, these fonts are so good, they make them look like they're handwritten. I've got two kinds of lunar missions. I have what I call sorties, and I have what I call outposts. They could be human-tended. And I've taken some of these numbers from NASA design reference missions, and what I've done is I've taken the mass required to do these missions, and I've divided them into two quantities. There's what I call sophisticated mass, and these are things like computers and life support equipment, power systems, electronics, engines, these kinds of things. And then what I call dumb mass. And this is mass that you use simply for its chemical composition or its bulk physical properties. And these are things like air, water, propellant, cement, bricks, mortar, stuff that you need by the hundreds, if not thousands of tons in order to make an existence on the moon. So now, look at these two kinds of class of missions, sortie and outpost, and I've done estimates on how much of each of these masses you need in order to do the mission. And the important thing is there's orders of magnitude difference between the quantity of dumb mass versus the quantity of sophisticated mass. So if you're thinking about doing these kinds of missions, take the sophisticated mass from Earth and use the resources on the moon that you need by the hundreds and thousands of tons. Get these resources on location so you don't have to bring them with you from the Earth. Now, when I did this, I came to a dilemma. I wasn't sure which category we should put the crew in. Now, let's talk about the low gravity aspect of the moon and how that can help us in terms of its utility. And to dive into that, I'm going to have to go on a small diversion talking about how we make rockets to get off of Earth. And this is a Mercury Atlas. And that rocket right there on the pad is about 88% propellant. Gemini Titan, 88% propellant. Saturn V, 85% propellant, which means it's only 15% of everything else, which is the rocket and all the stuff and the crew members on it. Space Shuttle, 85% propellant. Soyuz, around 89 to 90% propellant. So you're starting to see a trend here. Rockets are mostly propellant and only a little bit of structure. Why is that? This gets to what I like to call the tyranny of the rocket equation. There's my ability to draw a picture of a rocket. And the rocket equation, it's a momentum balance on a rocket, and this was first done by a visionary scientist, Konstantin Tsiolkovsky, around 1910. And every rocket that ever leaves planet Earth uses this momentum balance to aid in its design. And so a rocket has two very important parameters. One is the rocket velocity, which we call delta V, and the other is the exhaust velocity. How fast does the stuff go squirting out the nozzle? And the rocket equation is in that little box. It's a simple momentum balance, and two inputs, the exhaust velocity and the rocket velocity, and one output. It's the mass fraction of your rocket that has to be propellant in order to navigate the delta V that you want in your rocket. And notice, in the rocket equation, there's an exponential, and exponential functions are great if it's interest on money you got in a bank account, but almost any other thing, exponentials really cost you a lot. So now, what I want to do is independently look at rocket velocity and exhaust velocity. So, the rocket velocity, or delta V, this is determined by where you want to go in a gravity field. And right now, there's only about 4 places you can realistically consider human beings going. You could go into low Earth orbit, you can go to the moon, you can go to Mars, or you can mess around between the Earth and the moon, which we call Earth-Moon cis space, like visiting near-Earth asteroids. And we are here on Earth, right? The X right there. Although last night when I was leaving here, there was some students outside doing some celebration, and I was thinking these students here at Rice are already in space. But most of us are still here on the planet. And to get into low Earth orbit, the delta V is about 8 kilometers a second. And to go to the moon, to land on the surface of the moon from Earth, is about 14. Mars is 16, and near-Earth asteroids are 12. And this is what you have to expand in your rocket if you want to get there. If you want to navigate in this gravity field, you have to expend this kind of delta V, or you just simply won't get there. Notice that going from Earth 400 kilometers up to low Earth orbit, that's over half the delta V required to land on the surface of the moon. And so the single biggest step is getting off of Earth and getting the first 400 kilometers out into space. And so I'd like to propose that the giant leap for mankind was not the first step on the moon, but it's getting from the surface of Earth into low Earth orbit. And after that, all the steps are still significant, but not as big as the first step. And also, notice the delta V required to go from the moon into lunar orbit, 2 kilometers per second. We will get to that in the future. So this is the delta V required to get to where you want to go in the Earth-Moon cis space. Now, let's look at exhaust velocity. And there's my picture of a rocket engine. You start off with the velocity is 0 for the reactants in the rocket engine. You have a heat of combustion. You burn your propellant, and it goes squirting out the exhaust, and that's your exhaust velocity. And you do a first law, a thermodynamic analysis. When all the chalk dust falls, you get this rather simple equation. Square root of 2 times the heat of combustion times 1 over the molecular weight. And let's apply this now to several categories of propellant systems that we can use for human transport. So, choice of propellant, that defines your exhaust velocity. And I've lumped 4 different categories. We have solid rockets, and it really doesn't matter what the mix of the propellant is. You always get around 2.7 kilometers per second. And then you have kerosene, oxygen, really good stuff. And then you have hypergalls, things like monomethylhydrazine or unsymmetrical dimethylhydrazine and nitrogen tetroxide. If you like chemistry, these are really neat things. I had a student friend of mine in college, and he would always describe the latest relationship with his girlfriend. He would describe it as hypergallic. Spontaneously combusts when you mix. And then there's hydrogen and oxygen. And that's one of the best rocket fuel. Actually, it is the best rocket fuel we have for rockets that can fly human beings. And there's a new propellant system coming up, methane oxygen, and it has a specific impulse, or it has an exhaust velocity of around 3.6 to 3.8 kilometers per second. So it's about halfway between hypergalls and hydrogen and oxygen. And this is all we have from chemistry at this point in time. We've maxed out what chemistry can give us in terms of exhaust velocity. And so think about this. Gravity fields determine how much delta V, and we as human beings can't do a whole lot about changing the gravity of planets. And exhaust velocity is determined by chemistry of our propellants. And once you max that out, there's not a whole lot you could do about it. And these are the two inputs into the rocket equation. And you pretty much have to just go with whatever the result says. So what I'm going to do, I'm going to take these two inputs, plug them into the rocket equation for going from the surface of Earth into low Earth orbit. Let's look at the results. So, rocket results for low Earth orbit. 4 different propellant systems, propellant mass fraction of the rocket to get just that first 400 kilometers up. And you could see it ranges from 83% to 96%. And this is a very simple sophomore university level approach. No losses from the atmosphere, perfect combustion, no nozzle losses, single stage to orbit. Rocket engineers, and I don't want to say rocket scientists because rockets are made by engineers, not scientists. Rocket engineers could sharpen their pencils, you could do multi-staging, you could change the propellant from one stage to the other. There's all kinds of neat things where you could do a gravitational lean to convert tangential radial velocity into tangential velocity, which is really what you need for orbit. And there's all of these tricks that real rocket engineers can do, and you can beat these numbers a little bit, and you can see Saturn V, Shuttle, and Soyuz. Those are the actual numbers that these real rockets have, which are surprisingly close to this simple and naive approach of a sophomore level approach to using the rocket equation. This is the reality of getting off of planet Earth. Now let's look at the implications to this design. And so I've got several categories of vehicles. I've got the Queen Mary, I've got my pickup truck, I have a locomotive, and these are examples of surface vehicles. Okay, these vehicles are less than 10% propellant, and these vehicles are made out of billets of steel. If something doesn't work right, you go to the junkyard, you get a chunk of metal, and you weld it on the side of your pickup truck, and you keep going down the road. There's a robustness in your vehicle design when it has such a low mass fraction of propellant. Now, you look at aviation, fighter jets, cargo jets. These vehicles are around 30 to 40% propellant. That means they're 60 to 70% structure and payload. And now these are lightweight structures. You really have to do your engineering in order to make these structures work. And you just can't wantonly drill a hole through a wing spar because you want to hang a bracket there. You got to do your engineering. But in spite of that, we have an incredibly robust aviation industry. We could fly airplanes all around planet Earth. In fact, we can have strawberries in January. Have you ever thought, why can you go to the grocery store and get strawberries in January? It's because our aviation industry is so robust. We have excess capacity. We can fly strawberries from the Mediterranean or strawberries from South America in January to places that are packed with snow and ice. And that's because we have this robustness in our aviation industry. Now look at rockets, 85%. They are not even in the same category of vehicle. They are closer to explosive devices than anything else. Now, I knew this fellow that happened to have flown to the moon twice. And he told me once, he said, sitting on top of a rocket's like sitting on top of a Molotov cocktail. So I had to figure out what the mass fraction of a Molotov cocktail was. So I got a bottle of wine and I weighed it, and then I emptied the bottle of wine and I weighed it again, and I see there are people here doing that very demonstration. And then I had to compensate for the difference in density between wine and gasoline, which in this case was not a whole lot. And when I determined the mass fraction for a Molotov cocktail, it's 54%. So sitting on a rocket, getting ready to launch into space from planet Earth is worse than a Molotov cocktail. So, to recapitulate, the tyranny of the rocket equation. This is what I call the tyranny because it involves the magnitude of gravity in planetary bodies, which we have no effect over. It involves energy density and chemical bonds, which once we max them out, we can't get any more. And so we have land and sea vehicles, less than 10%. We have aviation, 30 to 40%, but it's a robust field. And then we have rockets, 85 to 90%. And rockets are on the edge of our engineering ability to even build, and on the edge of our ability to even afford to build. But what about moon? What happens if you apply the rocket equation to the moon? Here's the result, 40%. So if you have a rocket on the moon and you want to go into low lunar orbit, or go from point to point on the moon as a transportation source, 40%. So think of that. Rockets flying on the moon are closer to aviation is on Earth. And we've developed a robust aviation field on Earth. So I predict that if we return to the moon, because of its low gravity, because of the resources there, we will be able to have a robust vehicle infrastructure on the moon similar to what we have here on Earth, simply because the mass of propellant compared to the structure that you were flying falls within the realm of vehicles that we can conveniently deal with. It's not this absurd 85% propellant, 15% structure and everything else. So, this gets back to the moon, it's useful. I've talked about the resources to use, I've talked about the low gravity. These two things go hand in hand to make the moon a useful place to go to, as well as interesting, and it's close by. What I'm going to do now is talk a little bit about the resources. And this involves going to the South Pole region of the moon, what we're currently talking about doing, targeting for the Artemis missions. So here's a picture of the moon. It's from a view we're not used to seeing. It's looking at the South Pole. And the moon, its axis of rotation is almost aligned with the orbital plane going around the sun. So as the moon rotates, the North and South Pole have very low angle illumination. And if you happen to have a crater near the North and South Poles, the bottom of the crater never sees the light of the day. It's permanently shadowed. And these permanently shadowed regions, since all they see is the view of space, these permanently shadowed regions have temperatures around 50 Kelvin. So they're really, really cold. And these regions, over not geologic time, but planetary time scales, can cold trap volatiles, particularly water. And we now know, we didn't know this during Apollo, but we now know that there is water in these permanently shaded regions, along with a whole host of other yet to be identified low molecular weight, volatile organic compounds, and the tenor, the magnitude of this resource is estimated at millions of tons. And it's distributed between the North and the South Pole. Now, here's a close-up of the South Pole region. And the little arrow shows right where the true South Pole is. And there's a couple craters there. One is Shackleton crater, named after Ernest Shackleton. And then the other one is de Gerlach. And there's a whole host of all these other craters there. And the same thing can be said for the North Pole. Now, we know which of these craters have permanently shaded regions, and we know where the volatiles are. So the little red circles, actually they're red on my display, but they're just whitish looking circles there. These circles show verified areas of permanent shaded regions. We call them PSRs. NASA has to have an acronym. And another fascinating thing about the polar regions is that, and that shows up here in this little extraordinary graphic. Now let me go back one, okay? Now notice the difference between, that's just regular illumination, and see those brightish areas? That's integrated over a lunar year. So in the polar regions, there are areas of permanent sunlight, or nearly permanent sunlight. These high regions next to these craters can have 200 plus days in a row of sun, followed by maybe 2 to 6 days of darkness, and then another continuous period of sun. So this is an engineer's dream, because you've got an area of near continuous solar flux at 1,300 watts per square meter, right next to an area of continuous darkness at 50 Kelvin. And, engineers really love heat temperature differences, because if you got a high temperature and a low temperature, you can make a machine that works between those, and you can get work, and you can make a garden in that area. And so just from a resource point of view, the cold source of these craters, coupled with the solar power, could be an incredible resource, also coupled with the lunar material that could be used to make bricks and cement and mortar and radiation shield. And then there's the water resources that could be used for not only life support, but also for rocket propellant, one of the best that we know of for human transport. And then there may be a whole host of organics in there. Now, this is a little pasted area, and this is a map produced by the Lunar Planetary Institute, not far from the Johnson Space Center. And it shows slopes near the polar region. And let me blow that up. And all the blue areas are slopes less than 10 degrees. And the yellow and the red areas are slopes that can be above 10 degrees and even more than 15 degrees, 20, 30, 40 degree slopes. And you could see Shackleton Crater there, which we want to get to Shackleton Crater. It's considered a fairly small crater. We want to get to Shackleton Crater and look at the rim of that crater. There's a little bit of blue around the rim, maybe 100-meter wide rim that would be flat enough to land. And think about the lunar lander we're currently looking at designing has to land in the blue areas. If it lands in the red areas, it's going to tip over. And if it lands in the yellow areas, it might tip over. And so we need to target these blue areas. And you can see where we want to go, in the areas of permanent sunlight or near permanent sunlight, next to the areas of near permanent or permanent shadow. It's pretty rugged terrain. And we may have to find a compromise area where the ruggedness of the terrain will allow us to land a vehicle, but still be close enough to these permanently shadowed regions. Now, we think that Shackleton Crater, it's considered a smallish, medium-sized crater. And it's going to be loaded with volatiles. And there's a bunch of smaller craters there, but it's like, wow, let's go to Shackleton Crater, has been the cry of engineers since we've started to work on the Artemis program. Let's take another look at Shackleton Crater. Remember, it's a smallish crater. It's the size of Houston. And this is a plot made by David Kring. He's one of the lunar planetary scientists at LPI. And we may think Shackleton is small from all the other craters we see on the moon, but it is really a pretty big structure. And we're talking, we want to land on the rim and then walk down in there and take a sample of this stuff and then figure out how to mine it. David made another little comparison. There's Shackleton Crater compared to the Grand Canyon. Now, how many people here have stood on the edge of the Grand Canyon? Okay, it's an amazing place to stand on. And now imagine that you're in a spacesuit that maybe could be able to walk down a 20-degree slope, but instead of standing on the edge of the Grand Canyon, you're standing on the edge of Shackleton Crater. So it's really easy to talk about going to these permanently shaded regions, going in there, mining all these millions of tons of water, ice, and other volatiles. The actual engineering behind it is going to be really, really challenging. And if you go to Colorado and you look at some of these mining districts there, and you'll see a cliffside and a little ledge on the cliffside, and there's like 3 tons of steam engine left over from 1880 sitting on this little ledge. And you wonder, how did these guys, and probably gals, get that steam engine up to the side of that cliff and mount it there so that they could go ahead and do their mining? And we're going to have to use the same kind of ingenuity when we go to the moon. It may seem daunting now, but I have no doubt that when we get a lunar program there, when we have a significant presence on the moon, we will figure out from an engineering point of view how to deal with these kinds of things. We will start off small. We'll start off landing where the surface roughness and the slope angles allow us to get our feet wet at dealing on the moon. And there will be smaller craters that you can walk into that are permanently shaded. They may not have the vastness of the reserves, but we can sample them and get the chemical compositions and figure out ideas on how to mine these things. But eventually, we're going to have to figure out how to get into these craters, like Shackleton Crater, and figure out how to use these resources so that we can fully utilize the usefulness of the moon. So, why the moon? I like to say it's the next logical step. It's close, it's interesting, and it's useful. It's going to be a heap of work to really get there and to utilize this stuff. The South Pole is a rugged environment, but it's very enticing because of the power resources, the cold sinks, and all the volatiles that are there. And these are the things that we need in order to break the tyranny of the rocket equation, so we don't have to bring everything we need from planet Earth when we go exploring into the solar system. So Kraft-Ericke was really clever when he made his quote, because think about it, if we did not have a moon, it would be Venus or Mars, first step away from Earth. And the moon for space exploration is like the Mediterranean was for oceanic exploration. You learned to sail the Mediterranean first, and then you ventured across the Atlantic Ocean. Without the moon, it's like day one, get in your boat and sail across the Atlantic Ocean. So we are fortunate enough as a planet to have a moon. Another philosophical thought about planet Earth and the rocket equation. I took the rocket equation and I worked it backwards. I increased the size of Earth to the point where it would no longer be practical to get a rocket off of Earth. About 10, maybe 15% larger. So we are fortunate enough as a species to live on a planet that is just barely possible to get off. If Earth were bigger, we would be a single planet species. And the history of life on Earth is that of extinction. Think about that. History of life on Earth is that of extinction. If we were a single planet species, we know what the end result is going to be. Since we can actually get off of Earth, it's possible for us to open this petri dish of Earth and we can contaminate the rest of the solar system. And with that, let me close with this happy note that we can spill out into the rest of the solar system, and the moon is actually a logical step. It's an enabler for allowing human beings to get off of planet Earth using rockets, and maybe there will be a generation that's really, really bright and they can figure out a different way to get off of Earth and a different way to explore space. Thank you.
John has agreed to answer a couple of questions if you have any questions.
Yeah, so questions, anyone? Yes.
John, you did mention things like helium-3 and other useful substances you might want to bring back.
Yeah,
Sorry, it's okay.
yeah, Jeff asked about...
The question was, he didn't talk about it. I know he had limited time, but he didn't talk about helium-3 and some other potential substances on the moon that may be economically viable for us to get back to Earth that might make the trip worthwhile.
Yeah, there's a whole host of resources on the moon. Helium-3, which is exceedingly rare on Earth, can be found in some natural abundance. It's still pretty low. It's about 10 parts per billion in the lunar regolith. So to actually get huge quantities or useful quantities of helium-3, you have to be able to strip mine on a scale that makes open pit copper mines in Arizona look like it's small time. But it is possible. That resource is there, and eventually we'll know how to use it when we bring it back to Earth. Right now, we could have a big dewar full of helium-3 sitting right here, and we don't know how to use it in terms of getting energy out of it in a practical way. Eventually, we will. Helium-3 could be a driver for lunar resources, and particularly something of value on Earth. Jeff?
Yeah, so the one way to get rid of the tyranny of the rocket equation is by a space elevator. And Arthur Clarke said that when we finally build a space elevator, that's when humanity will become an interplanetary species. Any comments on space elevators?
Space elevators are wonderful. And guess who was the first visionary to talk about space elevators. It was Konstantin Tsiolkovsky, probably around the same time period, 1910. And for Earth, you need to have a beanstalk, call it a beanstalk, a rope going from geostationary orbit 23,000 miles all the way to the surface of Earth, and then you need a balancing beanstalk to go 23,000 miles the other way. And right now we don't have a fiber strong enough to do that. However, on Mars, because it's 3/8 gravity, it still has a rotation rate that puts geostationary orbit or Martian stationary orbit closer than Earth. We are within about a factor of 3, factor of 4 of having a fiber of sufficient strength to make a space elevator for Mars. And one of my favorite series of science fiction stories, Kim Stanley Robinson, has a trilogy, Red Mars, Green Mars, Blue Mars. And in his trilogy, he actually had a space elevator built for the use on Mars, where currently on Earth it's still way beyond our ability. And with the low density Martian atmosphere, in concept, you just have this rope coming down from geostationary orbit, and it just touches the surface of your planet, and you literally climb up the rope, and the next thing you know, you are at geostationary orbit. It's a wonderful concept. Konstantin Tsiolkovsky's.
I'm going to follow that one actually then, Don. So if we're within 3 or 4 factors for a space elevator for Mars, then we must be pretty close on for the Moon already then, right?
Moon is actually harder because it has such a low rate of rotation. The geostationary orbit for Moon is way far away. So an elevator for the Moon is actually more difficult than Mars.
And I did want to follow before that with, so if you're saying that if you're 10 to 15% bigger, the mass fraction is too small to be useful, does that mean all these exoplanets we find that are super Earths basically have no possibility of spacefaring life on it?
Yeah, if you like the anthropic principle, which is basically a philosophical construct where you say we have a sun of the right temperature and a rocky planet the right distance with the right amount of water and yada, 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 and it sits there and cooks for enough time, and here we are with some level of intelligence, at least enough to contemplate that, oh gosh, here we are. And you can add one more rung to the anthropic abstraction ladder by saying that we are also on a planet that is just barely possible for us to get off, and which might ensure our survivability, of course, assuming we don't kill ourselves off without help of Mother Nature. So I do think this is fascinating, and when we see these exoplanets, if you get a dense exoplanet, or maybe one that has a larger radius than Earth, or maybe a thicker atmosphere, there may be intelligent species that have evolved there, and they can't get off their planet. And we are fortunate. I've heard, I saw a T-shirt where it said, "One planet is not enough." Any other questions? Okay.
I was just wondering what the quantity of volatiles that we anticipate being located in the South Pole for the mining purposes. Is it considered a limited resource?
The quantity of volatiles, I have heard numbers estimated, and these come from the Lunar Reconnaissance Orbiter. They come from 5 or 6 different probes that we've sent to the moon since Clementine in the mid-1990s that first made a measurement that showed that there was water in the poles of the moon. And the estimates for quantities vary, but the last I saw, people were estimating that there's millions of tons of water distributed fairly equally between the North and the south lunar poles. So I think there's going to be enough resources there so that by the time we've consumed all of those, maybe we will have developed a technology so that we don't need lunar water anymore for propellant.
But also in high concentration?
We don't know. It appears to be in ice form, and we don't know, is it 10% mixed with the regolith? Do you have this powdered granules and it's only a little bit in the regolith? These measurements basically show bulk properties, and you can estimate the tonnage, but there's a lot we don't know about the state of the water. Is it just sitting on the surface? Is it intermixed in the regolith? How deep does it go? We won't know that till we get there and start sampling, which should be one of the high priority surface science objectives for returning to the moon, is first figure out what is the composition of this stuff and what kind of organics are in it. And we know there's a bunch of other stuff in there that might be useful. And then looking at how is it distributed in the regolith and in what form. And then we can start putting on our thinking caps and figuring out how to go into these craters. And for those of you who are thinking about spacesuits, what's going to happen to your spacesuit if you walk into a crater that's 50 Kelvin? Have you seen it where you dump like a rose in a beaker of liquid nitrogen, and then you crush the rose, it crinkles into powder. So what's going to happen to your spacesuit when you go into these places? Again, engineering details that we can put on our thinking caps, and we can figure all these things out, and it's only going to take time and money. And of course, we've got plenty of time, and we'll have to see what Congress does and what happens with our international partnership in terms of going on this adventure, because this is certainly something that we cannot do alone as a single country. And these are resources that really belong to humanity, and we need to do this in an international way, like we're doing with the International Space Station.
Don, also you said it's interesting and useful. Have you also looked at the angle in terms of what you can do on the moon that we can't do here? So for example, on South Pole Station on Earth and in Arecibo, we can do some pretty interesting observations. James Webb is struggling right now. So what sort of telescope could you build on the moon at 50K and observe from there?
There was an astronomer back in the mid-90s, Jack Burns, and he proposed a whole suite of astronomical telescopes that you could build on the moon, both near side and far side, and had all this justification for why you would want to do this on the moon. So people have thought about that. I can't recite all of that stuff off the top of my head, and I just have to kind of dodge the details by saying smart people have thought about this, and there are other things that you can use the moon for besides just its resources or doing scientific investigations about the moon. Okay, going, gone. Thank you all.
Thank you, Don. Thank you, Don.